Hi, chemistry class. Today we're going to talk about different shapes of pH curves. We'll talk about some different reactions. We'll get into indicators. Now that we're done with the titrations, most of the math, pretty much all of the math in this unit's behind us. And there's not a lot of math in the next unit, so maybe you can look forward to that. We had a test coming up I want you to be aware of. Sign up for the tutorial I mentioned in the classroom stream. But let's get into this lesson now. So strong acids react quantitatively with hydroxide. We already know that. pH curves demonstrate that many weak acids react quantitatively with hydroxide, and that some weak bases react quantitatively with hydronium. The way we'd be able to see that is the steep part of a pH curve. If there isn't a quantitative reaction, you don't get that really, really steep region of a pH curve. You just get a gradual increase or decrease in pH. Furthermore, using an indicator, you don't get that dramatic and cool color change if there is not a quantitative reaction. Okay, so now I want to talk about the three types of reactions that can lead to a quantitative acid-base reaction. The first one is the simplest one, a strong acid, strong base reaction. Okay, so as an example, mixing nitric acid with sodium hydroxide, I've gone ahead and written down the entities present. So what we're going to do is predict the acid-base reaction, which we have some experience in doing. So just recall a strong acid ionizes completely with water. So what you actually have in solution is hydronium. Nitric acid also has this nitrate ion kicking around. Sodium hydroxide dissociates into sodium ions, hydroxide ions. It's all taking place in solution. So what we do is we go through our data booklet, table of acids and bases, but I'm hoping nobody needs to for this example because we've got hydronium and hydroxide. There are no other options. So our net reaction looks like this. No surprises at all. Remember, I'm only using examples of quantitative reactions. You don't need double arrows. What I want you to notice here is when the reaction takes place, the product is water. Okay, so at like the equivalence point, when there are equivalent amounts of each reactant, only H2O is present. That means that the pH is going to equal 7. That's a neutral pH. Okay, and I'll show you what that means in terms of pH curves. It's the pH curve you've already seen, but let's move on to some more interesting examples. Okay, so here, let's talk about a strong acid, weak base. So hydrochloric acid with ammonia. All right, I've already listed the entities. Again, strong acid, you get hydronium, the chlorides kicking around. This is ammonia. Remember, if you have a weak acid or weak base, the entity you write down is just that weak acid or weak base. So just heads up, you don't need to walk around knowing what ammonia is. You can Google it, of course, we're all at home. You can look it up in the molar enthalpies of formation. It's right at the top there. And I'm thinking you'll see it in the table of acids and bases as well. It doesn't actually come out and say it. You would actually have to know that ammonia is the conjugate of the ammonium ion. Okay, so however you need to find out what ammonia is, whether it's Google or that standard enthalpies of formation, on a test I give you the formulas, so it's nothing to worry about. All right, going through my table of acids and bases, the hydronium is definitely the strong acid. None of these are going to be particularly surprising, so ammonia is our strongest base. Let's write down our net now. So again, quantitative, we're just going to have a proton transfer. All right, so at the equivalence point, we've got water, but we've also got ammonium, which is a weak acid. Okay, so at the equivalence point, we've got this ammonium ion, and I showed it to you earlier in the table of acids and bases. So this is a weak acid. So that means that this equivalence point, when you combine a strong acid and weak base, will occur at a pH of less than 7. Okay. we'll discuss the consequence of that in the next video. Moving on, weak acid, strong base reaction. Okay, so this time I'm mixing acetic acid with potassium hydroxide. So my weak acid is present, that's acetic acid. Potassium hydroxide dissociates, water's always around. But again, I'm not trying to confuse you here. These are strong acid, strong base. Let's see what our reaction is. Okay, so just do a proton transfer from the acid to the base. Looks like this. Oops. So this is the acetate ion. All right, I'll find it in the acid-base table for you guys. All right, looking. So here's acetic acid. Its conjugate base is a base. It's basic. Okay, we could do the KB thing if you want, but this is not polyprotic, or sorry, this is not amphiprotic. It doesn't behave as an acid at all. So we know that it's basic. So at the equivalence point, we've got this ion kicking around. Okay, so that's going to be a pH of greater than 7. It's pretty easy to remember. When you have a strong acid, the pH at the equivalence point is a little bit acidic. When you have a strong base, the pH at the equivalence point is going to be a little bit basic. Okay, if they're both strong, then the pH is neutral. One thing I want to mention, I should write it down, is we're not going to talk about weak acid, weak base quantitative reactions. They can occur, but they're difficult to predict, and it doesn't really fit in what we're talking about today, which you'll see in the next video with pH curves. Okay, I'll mention it in the next video as well. Okay, so just a reminder, strong acid, strong base quantitative reactions have an equivalence point at pH 7, okay, because they only form water. Strong acid, weak base, at equivalence point, it's weakly acidic, so it has a lower pH. Strong base, weak acid, equivalence point is slightly basic, so the pH is greater than 7.